Yes, I think we are live now.
Okay.
Okay, let's start. শুভ সন্ধ্যা সবাইকে. Good evening, everyone. Welcome to today's podcast, Cosmic Codex event by Cosmic Shared. We are thrilled to have you all space fans, astro enthusiasts with us as we embark on a journey through the wonders of the universe, exploring the latest discoveries and advancement in astrophysics and cosmology. Today, we are privileged to have a distinguished speaker with us. Please join me welcoming Dr. Ankush Sengupta with his session titled Statistical Physics for Understanding Dynamics of Living Systems. Dr. Ankush Sengupta is an assistant professor in the Department of Physics at Amity University, Kolkata. He holds a PhD from S.N. Bose National Center for Basic Science, Jadavpur University, and an MSc in Physics from Presidency College, University of Calcutta. Dr. Sengupta specializes in soft condensed matter physics and has extensive research experience, including postdoctoral positions in France, Israel, Germany, and the UK. His research interests include computational studies on active soft matter, self organization, dynamics, and the physics of driven disordered systems. So, before getting started to our main agenda, I would like to take a short note about our teams, our next visions and missions of Cosmic Chariot. So, you know that we have successfully published our first ever Cosmic magazine at Kolkata Book Fair in 2024. But now we are more excited to announce that we will be publishing our next issue, the Sharodiya Shankha, during the upcoming Durga Puja in October. So stay tuned and stay updated with us. We will give you a big update in coming days. So over to you, Sir Ankush Sengupta. You can start your session.
Okay. So good evening, everybody. Good evening, Shomrit,
Yes, good
for
evening.
organizing this event. Uh, Let me first share the PDF file. What was the? It was like present. No, I have to just go into the present
Yeah, I am
and then share
stop sharing.
screen.
You can share now.
Yeah, just one moment, yes.
Yeah. And to the audience, I would request to give a like button, press the like button of the YouTube so that you can get more engagement from us.
Okay. So
So whoever is
share
watching, please press a like button on the YouTube channel.
screen. Okay. Hello. Uh, Single window. Entire screen maybe. Or single window. Okay. Share. Is it getting shared? Can you check?
Yes, yes, it's shared.
Yeah.
Yeah.
Yeah. Okay. Okay. So we will be talking about the statistical physics and its use in understanding dynamics of living systems. Okay, and this Shambhit and Abhirup I will be doing it very briefly. It should not be a very long talk, and it would be nice if we can sort of have both Shomrit and Obiru somehow interacting yes, no, or something in between so that I don't feel a bit bored just talking to a screen. Okay?
Yeah, definitely, no problem.
Yeah. So the motive of this talk is to let people know. I mean, people in the sense not very. I mean, not the PhD holders or the postdocs or and so on, or even the faculties, but rather trying to let know the school leaving kids maybe and maybe the undergraduates and postgraduate students what is it like to work in statistical physics and how things can what is the scenario there and what should one expect while working on simulations and statistical physics and computational physics of systems which are a bit different from the everyday physics systems that we deal with, like non-living systems, but it should be like living systems. If we are addressing living systems, can physics somehow come to help there? So that is the brief motivation of the talk. So the outline. Oh, how should I go to the next screen? Next slide.
So normally, what you can do as previous, so you can just do that. You can control your PDF actually, so it will automatically reflect in the live session.
Okay. Like now, is it showing the second screen?
Yes, yes, exactly. Yeah.
Okay. So the outline of the talk will be like what is statistical physics? What do we do there? Because many school living children and the undergraduates in the preliminary years may not know what statistical physics deals with. And then what about dynamics of systems? How dynamics that we learn from school, how is it addressed in terms of statistical physics? And then systems that I will discuss are active matter systems, although that will be a very brief and preliminary overview of what I mean by active matter. So active matter basically includes biological systems, non-equilibrium systems where there is an energy input into the system which can translate to motion or other forms of energy, mainly motion. So those are the active matter systems I would like to address, maybe self-propelled colloids or even bacteria and cells and even higher organisms like birds and insects and so on, and how do their dynamics, how their dynamics can be addressed in general. Next, we will be coming to an example where there would be an agent-based modeling which can be possible to study the dynamics of swarming of like birds or bees or insects or the schooling of fish and so on, and how to address those in terms of physics. And the last example that we will be talking about, whatever the small things we learn from here, how can they be used to study a case of chemotaxis, which perhaps students have already aware of. Chemotaxis is a phenomena where cells or other living organisms show a response to stimuli, where the stimuli is a chemical. So how our understanding of statistical physics can help addressing pressing questions in these stories. Okay. So what is a statistical physics? Now matter as such consists of atoms and molecules, right? Shamrit and Avirup, if it's okay to interact a bit. So there's like atoms and molecules would be the
Sure.
smallest possible constituents of matter. And if I wish to sort of study any property of matter, those properties could be like electric properties, thermodynamic properties, mechanical properties, hydrodynamic properties, and whatnot. Even quantum properties. Then although in experiments we can study those properties by measuring them directly, but in order to build a theory out of it, that means at least to know how the constituent atoms and molecules they actually contribute to the measurement or to the phenomena of observing those properties, how they contribute to those properties themselves, would be a very theoretical questions where one has to bridge a gap between the macroscopic and the microscopics. So the microscopic particles like atoms and molecules, they move about within the bulk, and these dynamics following whatever equations of motion they wish to follow, they would follow. And when they move through them, this dynamics would contribute to the properties that we are measuring. For example, charges when moved, they constitute the macroscopic current that we can measure through an ammeter. Or when the molecules and atoms of a gas are banging around and banging on the walls of the container containing it, then that constitutes the macroscopic property of pressure. Similarly, the average kinetic energy of all the atoms and molecules constitutes what is known as the temperature of the system. I hope you all realize this from our school level physics. So, in order to see how these microscopic dynamics can be at least translated to reflect the macroscopic properties of matter is actually the essence of statistical physics, of studying statistical physics, to see how this works. Okay. So whenever we say that the macroscopic property of matter, we have to think in terms of moles at the least. So a mole, which is the smallest macroscopic, what I would say, drop of matter, actually consists, if you see, of Avogadro number of molecules, right? Like 10 to the power of 23 molecules. And then to describe the equations of motion of so many of them, we know the equations of motion. If I look at these atoms and molecules classically, although they are not classical, but if we can think of them as classical particles moving around, then I know that dp dt is equals to force is the equation of motion, right? So if I this is a differential equation where dp dt is equals to the force that is impressed on the ith atom. So that's why I have given a dp I dt is equals to fi. It's a vector equation, and this fi can consist of any external force acting on the particle as well as the particles actually interacting with all other neighboring atoms. You see what I mean? So there will be j atoms, j going from 1 to n, and there will be an fij. So fi external plus summation over j, j going from 1 to n, and of course j should not be equal to I because there is no self force. So Fij is the force between I and j atom, which are distinct, which are completely distinct. They are not the similar atoms we are talking about. And this is a differential equation. And once if we hope to solve this differential equation, the method we take help of is an integration, right? The differential equations are solved by integration, and the expected solution will be pi as a function of time. So this is a differential equation of time, so we will get the momentum pi variable as a function of time. Now, since I know that this the momentum is actually the mass times the velocity, if I divide the momentum by mass, I will get the velocity, and from the velocity I can use the other differential equation, which is dri dt is equals to vi, and integrate it in order to know the positions, since I know the velocities from the momentum. And then if I integrate this equation dri dt equals to vi, which is simply the definition of velocity, if I integrate that, I will get ri as functions of time. So this is how I can expect to get the full solutions of ri's and pi's as functions of time t. Okay, but the situation, although it seems very simple, is not at all simple, because you know the forces of interaction between any two I and j particles would depend upon the relative distance between them. So in order to get the relative distances, in order to calculate the forces, I need their positions of the I and j particle. But that is coming from the second set of differential equations dri dt equals to vi, which I need to integrate and solve, right? So unless I solve the dri dt equals to vi, I won't be able to get the ri's as functions of time, and so I won't be able to get the forces that are required in the first set of equations dpi dt equals to force, right? On the other hand, in order to solve the second set of equations dri dt equals to vi, I need vi, and the vi comes directly from the pi's, which comes from the first set of equations involving momentum. So you see, these two sets of equations are highly coupled with each other. It's not so simple that I say solve one set of equations and use the solutions in the other set of equations to get a clear kind of solutions of the set of Ri's and Pi's as functions of time. They are highly coupled. Moreover, if you see, there are n equals to 10 to the power of 23 equations to solve, at least of that order. So this is a horrendous task. So if you start from now on to solve those equations, you will spend generations after generations without solving them really, right? And after that you need to analyze those. So this is a completely an impossible task. You see. So since this is an impossible task, but we are all set to try to bridge the gap between the microscopics and the macroscopics. That means to try to see how the microscopic properties of atoms and molecules in terms of their position and momentum can actually contribute to any macroscopic properties. We have to take some other route. The solutions of equations of motion is actually next to impossible. So that is where statistical physics comes to some kind of help. So what it does in a nutshell, in a gist, is that since the atoms and molecules will be changing their positions and momentum over time, and these variables are functions of moment of time, these functions, the variables, positions and momentums are actually the functions of time. So therefore, the values of Ri's and Pi's that are frequented over time will have a probability distribution. Like these values of momentum for a particular specific system of interest that we are observing, these specific values of momentum are occurring too often than the other values of momentum. Similarly, those particular sets of position values are occurring more often than other possible values of position. For example, I can straight away give you a blunt, crude example, like the position of particles in a confined box. So if I have a box there and all the atoms are of the gas are within that, so there is no way I can get a value of the position outside the box. So the probability of finding the particles outside the box is completely zero. However, and if there is a strata of liquid within a gas, maybe due to gravity, the denser part has settled down at the bottom of the container, whereas the less dense part are on surface of the container. So you see, the particles are preferring more to be present at the bottom than at the top. So depending upon what situations you are using, you can assign a probability distribution of these microscopic variables, namely the positions and the momentum and the momenta of all these particles. So therefore, this probability distribution will be very helpful to calculate any kind of average macroscopic property to which they are contributing. How? For example, if I have a class of 100 students, and if I wish to calculate the average age of these students, I can do it in 2 ways. Sorry, yes? Any questions from there or something?
No, it was my mistake.
Okay, so for example, if I have a class of 100 students and if I wish to measure the average age or the mean age of this class, I can add the age of all the students together and divide by 100. That's the number of students. So that will give you your mean age. On the other hand, I can make age brackets, like age brackets 1 to 2, 2 to 3, 3 to 4 years, 4 to 5 years, and so on, and maybe 99 to 100 years or 199 to 200 years. And then within each age group, how many students are there in the class? For example, in a class, we cannot expect any students of age 1 and 2 in a graduate class, of course. So those distributions of frequencies will be zero. But there will be a crowding around maybe 18 to 25. There will be a crowding of students, and then there will be a tailing off at the ages. So I can get a frequency-weighted distribution, a frequency-weighted average age, which would also help me to find out the mean age of the class, right? So therefore, from this, if I can have some idea of the probability distribution of these microscopic variables, namely the position and the momentum of all the particles, that would certainly help me in calculating any average property of the system that depends on these two microscopic variables. Am I clear? May I ask Shomit if these things are clear or?
Yes, sir, it is clear.
Okay, good. So this is what statistical physics aims to do. It tries to find out a probabilistic approach to find mean macroscopic properties. Okay, so let's move on to the next slide, where I would talk of a very simple example. And this example would consist of a man. You can see the stick figure of a man there with a bottle of beer in his hand, and he is walking this way and that in a random fashion along a one-dimensional road. You see, in the middle of the night. And if I say where the lamppost is, if that is the origin from where the man has started walking, trying to go home, but walking this way and that randomly under the influence of the beer he has taken consumed. So there will be a probability that a man takes a right step and a probability that a man takes a left step. So there is a right step possible and there is a left step possible. If I say the intrinsic probabilities of this left and right step are small p and small q, and ideally if it is a completely unbiased random walk, then small p and small q both should be half because they should add up to 1 and they are perfectly unbiased. Half plus half should be 1 in that case. The total probability has to be 1. So out of a total number of capital N steps, walking steps that the man takes throughout the night, if there are nr number of right steps and nl number of left steps, then of course nr plus nl will be equal to the total number of steps n. Similarly, if I wish to take a difference of nr minus nl, that should give me the distance of the man from the lamppost. Has he moved towards the right? Is there a net movement towards the right or is there a net movement towards the left? That would depend upon the sign of nr minus nl, which I call small m. So the sign of m will determine whether it is moving right or left, and the magnitude of it will determine the displacement, the amount of distance he has covered either to the left or to the right. Okay. Now, since he is taking nr number of right steps, each with probability p, so p to the power of nr and q to the power of nl should contribute to the probability of finding the person at a displaced position m from the origin. And since there are nr right steps that can be taken from n steps, there can be ncnr number of combinations possible. That means how many ways I can choose nr right steps out of n steps, which is NCR, that is n factorial by nr factorial into n minus nr factorial. So this, when factored together, when they're multiplied together, would actually give me Pn of m. You see, and that is the total probability distribution we are talking about of finding the man at a displaced position small m after a total number of capital N. So capital N actually translates to the time. Since this is total N is the number of walking steps, it should translate to the time, and small m should translate to the displacement of the system. Thus, with the help of this probability distribution, I can find average properties like the average displacement. And although I have not shown you the full calculation here, I mean that can only be done in class, not in a talk like this, in a podcast like this. One can use these expressions to calculate the average displacement when the P and Q, both of them are same, that is half, and one would get an average displacement of 0. And an m square, there is a mean square displacement proportional to the time step n. Okay. So if I actually talk in terms of not the m and n discrete variables, but in terms of the position x and the time t, then I will see that the average displacement, average x, those angular brackets actually means we are calculating averages, and the mean square displacement I can get. So mean displacement turns out to be 0, and mean square displacement turns out to be proportional to the time t. You see? So what it actually means when the probability of taking a right step and left step are exactly equal, then after walking all through the night, after walking through the night, it's the man is almost has reached nowhere. He is actually loitering somewhere around the lamppost. The mean displacement is somehow 0. You get it? Sorry. Yeah. So now going to the next slide. So if I try to solve this problem for a very large number of n, remember n could be very large. Remember that when n I was talking about in the previous slide was a number of atoms and molecules, although here n represents time. So n, if it refers to a large number of atoms and molecules, it was of the order of 10 to the power of 23. Again, if I view n as time, time could be a very long time, because when I measure a macroscopic property in an experiment and I take readings and average those out over time, then those readings may be over time scales which are like the order of microseconds or milliseconds or even seconds. Whereas by that time, the atoms and molecules within a constituent gas or solid or liquid, whatever, has moved so many times, has moved from here to there so many times. So in terms of the atomic and molecular time scales, the time scale of macroscopic observation could be very large. So therefore, in this very large n limit, that means long time observation limit, these kind of calculations can pose similar problems, because you see there are factorial n's to be calculated in the calculations, right? So there is a way out where we can give an analytical version of log of factorial n, which is called the Stirling's approximation, and it states that log of factorial n is something like n log n minus n, as an analytic expression which is easier to handle with while doing the mathematics. And with those approximations, your probability distribution, which I have just written at the end, the last two lines of this slide, shows that it is approximately a Gaussian with a proper normalization constant. That should be taken care of because we have made some approximations there. Okay. So it is a Gaussian. So you see on the top right corner of the slide, I have drawn. Although it's not very symmetrically drawn, but it should be symmetric. It's like a Gaussian. It's like a bell-shaped curve, which shows that the maximum probability of finding the man or the particle will be somewhere near the origin. And as I go far and far away from the origin, the probability diminishes, tails off, as you can see, right? So this is all about how to calculate probabilities in the context of a random walk problem. But why at all should this be useful? Why should all these things be useful? Any ideas from the other side? Why should I be at all interested in a problem like a random walk of a man in one direction and calculate the probabilities? Any idea why should this be helpful in the context of physics? Shumrit and Virup or any others.
Predict the motion of the man.
Yeah, this is for the man, but in context of physics. In context of physics, for example, you see Brownian particles like pollen grains in water, they move in a complete random motion, right? They get kicked by molecules of water and they do a Brownian motion. I think we have read about those in school, right?
Yeah.
So therefore, when a colloid-like particle, a particle which is of the size of a micron size particle, is given in water and it is moving around, being hit by millions and zillions of molecules around them, right? And then there is random forces acting on it. So the way it will move is not at all systematic. It's not at all deterministic. It is completely chaotic. It is completely random. And this zigzag motion, which is called the Brownian motion, can be addressed by this sort of problems. Okay, so this is why this could be very useful. Okay, moving on to the next slide. So this is what I have actually described in the slide. You see, particles, as I said, which are mesoscale. By mesoscale, I mean of the sort of microns, of the order of microns, micrometer size, 10 to the power of minus 6 meters to say. Yeah. So those particles, if I take the surface of that particle, of a particle which has the radius of maybe 1 micron, then over those surfaces it can accommodate zillions of molecules, and we can do actually the calculation to see how many, depending upon the size of the atoms that we are talking about from the fluid, how many particles or atoms of the fluid a micron size object can accommodate on its surface. For example, you know, bacteria, virus, these particles, these are like micron. This could be micron-sized particles. Even amoeba, they could be tens to hundreds of microns, even to thousands of microns. So therefore, when they are in water, they are constantly being bombarded by atoms and molecules of the liquid environment around. So the task of getting from this point to that point by a bacteria or by an amoeba is not so easy. You see, they're being kicked around by these atoms and molecules. Okay, in terms of the energy they have. You can imagine. Although we can do certain calculations, but it's beyond the scope of this talk. But you can imagine that their life is hard. So someone has a question there, maybe. How do random walk models help in understanding transport properties of ions and small molecules across cellular membranes? Well, that's a very good question. Should I answer this right away?
Yes, sir.
Okay. So if you go back to my previous slide, where even before that, maybe here, who's asking that? May I know his name or? Ovirup himself is okay. Ovirup is asking. So you see, Ovirup, here you see this dpi dt is equals to an external force plus summation over interaction forces. Can you see that? The interaction forces between ith atom and the jth atom. Now here you see the external force will be the force acting on the ith particle. So when we have these ions and molecules which are getting transported from one side of the membrane to the other, these ions are actually subjected to an electric field gradient in direction of which it is moving. So these external forces will be the Fi external that I have explicitly written on those equations of motion, you see. And when I can substitute that, and I know if I know the potential, the electrostatic potential, I will just do a minus gradient of V, and that will translate to the force, the electrostatic force that will be acted on by the electric, that will be acted on those atoms, on those ions and small molecules, charged molecules. And this would help them to go from one part to the other. This is a kind of a transport which is biased. In this case, of course, the random walk will not be completely random, because here small p and small q will not be the same. Either p will be greater than q or q will be greater than p, depending on which there will be a net flow towards the outer side or inner side of the across the membrane. You see, so this is how active transport can take place, can be addressed. I mean, although I'm telling it in a very sketchy way, there are much more details in it. But to help you to understand, this is how random walk can help, a biased random walk can help you to address this kind of problems. Okay? So, okay, good. So, let's move on to what we are now doing. So, now, as I said, that if I have a Brownian particle, like a, okay, okay. So if I have a Brownian particle of a size of a microns moving inside a fluid, that is a kind of trajectory that I have drawn, and that is from a computer simulations that we have done in our classes. That is a kind of trajectory that a particle can follow. You see, it's a very crowdy, random, haphazard trajectory, zigzag motion. That's what Robert Brown has described it, and later on, Paul Langevin has given an equation of motion to describe such particles. You see, m dV on the left hand side of this equation is actually the rate of change of momentum. If m is constant, it is like ddt of mv is a momentum, right? And that particle, Brownian particle, when it is moving inside a fluid, it is of course feeling a viscous drag, which is proportional to the velocity. So the force that it experiences, one of the contributing force will be the viscous force, the viscous drag, which acts in the opposite direction and is proportional to v. So the first term is something like minus v with a 1 by b, where b I call mobility, or 1 by b I call is the friction coefficient or the viscous coefficient or the viscosity, something related to the viscosity, okay, the viscous drag, okay. So minus 1 by b times v is a viscous force, plus there could be forces of interaction of one particle with other kind of Brownian particles, not the atoms and molecules here I am talking about. This is the third term I am talking about. The third term, summation over j, f j of t, is actually the force from any other Brownian particles j on the particle of interest that I am trying to move around, okay, that I am trying to, whose dynamics I am trying to study. And the second term, which is eta of t, that is the random forces that are acting on the particle due to the atoms and molecules within the fluid, and that is completely random. So eta is the resultant of all the bombardments, the atomic and molecular bombardments that this Brownian particle is suffering being embedded inside a fluid. Okay, so all these three forces together constitute the rate of change of momentum as per Newton's law. Okay, so if this is again another differential equation, so if I can integrate it, solve it either analytically or do a computer simulations of that, I will get the full trajectory of the particle, and also I will get all the velocities and of the particles. So the momentum and the positions will again be completely chopped out or tabulated, and then from that I can get whatever property I wish, provided the number of particles are small enough, number of collection of Brownian particles is small enough. However, although the number of collection of Brownian particles is small, or 1 or 2 or 10 or 5 or 500 or whatever, but the number of water molecules around in the fluid will be at least 10 to the power of 23. So since we are not going to take into account all the detailed deterministic dynamics of all these atoms and molecules, we see that the force theta, which is a random force, has certain characteristics, and by characteristics I mean its distribution characteristic. For example, the average of theta should be 0, because the molecules can bombard from this side to that side, or this side and this side equally. So the average of this random forces should be 0, and the mean square of this random forces would be related to the kinetic energy that so somehow should be related to the kinetic energy of the of the molecules, and therefore should be related somehow to the temperature of the system. You see, so the eta of t and eta of 0, this correlation, or the eta square, the strength of this random noise should be such that it translates to the temperature. You know that more vigorous these bombardments are, the temperature will be more, because if I have a higher temperature, the molecules will be more agitated in a state of vigorous motion, and therefore the strength of this random noise should somehow be reflected from the temperature, should somehow reflect the temperature of the system. So given the temperature, I can even model this kind of random forces and then try to work with them in order to understand the dynamics of the system. And this is some analytical calculations, which I think for the dearth of time, because otherwise things will get too long. You see that if I can solve this equation, the previous equation, this differential equation analytically, I can do it, and I will get the mean square displacement, and this will be an analytical expression of this form. And for short time scales, I will see that the mean square displacement scales as proportional to time, whereas, the mean square displacement is proportional to time square, whereas for large time, the mean square displacement is proportional to t, you see? Okay, so any questions? Any questions on this, or?
Yes, sir. One question has
Yes.
come. I am
Yes.
showing in
In
the screen. So can you see?
Okay. In what ways can the study of phase transitions in statistical physics aid in understanding the transitions between different states of biological systems, such as the differentiation of stem cells? Okay, this is something I will come to in next few slides, and then I will answer that question. Okay, so in the next few slides, I will precisely be talking about this, how phase transitions in statistical mechanics can be actually helpful in understanding dynamics of cells and cell differentiation and so on. In some nutshell, I will be coming to that. Okay.
Okay. So
By the way, how much time do I have? Obiru, how much time do I have?
sorry.
How much time do I have?
So you have another 15 minutes, sir.
Oh, okay, so I have to hurry. Okay, what roles does entropy production play in random walk models of active matter, such as movement of bacteria or cytoskeleton? How can statistical physics quantify this? Okay, this is beyond the scope of this talk, because this, as I said, this is a talk addressed to preliminary years undergraduate students, maybe undergraduate students overall, and preliminary years postgraduate students. Not really. So these questions that entropy production and so on would be actually addressed, can be actually addressed in much more details, with the help of much more detailed calculations. But nonetheless, in order to just say about the entropy is what? Entropy, you know, is actually the measure of randomness in the system, right? It's a measure of disorder in the system. So it's a measure of disorder in the system. As I say, the position and momentum values of the microscopic particles, these are randomly distributed. So if I can somehow get a measure of this random distribution, that means the fatness of the distribution of these microscopic variables, that should translate to something of an entropy. Okay, so this is a very crude way of addressing this, but nonetheless, this is one way of addressing the question. And how it affects active matter and so on, that will be that I won't try to address here. That needs much more involved talk. Okay. So going over to the next slide. So this, you see, I have drawn the mean square displacement as a function of time in a log-log plot. And what I see is there is a transition from t square behavior to t behavior. You see? And these can be actually captured from computer simulations of Brownian colloids, just following the Langevin dynamics equation that I have shown you. Okay, so I won't go into this, but as you know that since we are dealing with one particle, now I can actually connect more than one particle, for example, if two particles, Brownian particles, are somehow connected by a spring, then that should act as a dimer. And then we can study the dimer. So here, what I have tried to study is the kinetic. I've tried to show you here is the time dependence of the kinetic and the potential energy of a dimer and the total energy. You see, the total energy remains fixed, whereas the kinetic energy dips at a point where the potential energy peaks. So that means the total energy has to be conserved. Okay, and then the mean square displacement again of the dimer as a function of time is down, and we see that there is a crossover from a super diffusive t square behavior to a diffusive t behavior. Okay, so in this way we can study even polymers when we connect more than one particles by springs. And you know, DNA and RNA and cytoskeleton someone was talking about are polymers with different stiffnesses, although there are much more complications there, but basically they are polymers, and those can be modeled with the help of these Brownian dynamic simulations to give you some kind of a feel of how things work. And this is, we see from one of our simulation studies, there is a polymer and it is moving around in the environment inside a fluid, and you see at very low temperatures on the right hand side, the dark one, which have low velocities, as seen by the color bar of the velocity scale there, at low temperatures they try to shrivel up. Whereas at high temperatures they try to extend. So this kind of transition is called a globule to coil or coil globule transition. And this is a type of phase transition. Someone was talking about phase transition. So these are kind of phase transitions that is happening inside a polymer. For example, an RNA, a single-stranded RNA can show this kind of phase transition from a very globular compact state to a very extended coiled state. Okay, so this kind of phase transitions can be worked using with the help of statistical mechanics. Okay, or statistical physics. Okay, another example why this the random walk thing that we are talking about. If you remember, there was the man could either walk this way or that way. That could also be helpful in addressing questions like a magnet. You know, the magnet a magnet consists of what? Of microscopic magnetic dipoles. We know this, Ovirup, right? Ovirup or Shomrit, we know that a magnet is actually composed of atomic dipoles. And the dipoles can point either this way or that way. So if I have a two-way pointing dipoles, two-state dipoles, which is pointing either up or down, then I can see if there are capital N number of atoms there or atomic dipoles there, then there will be n u number of up atoms and up dipoles and d number of down dipoles. So that nu plus nd will give you the total number of atoms or atomic dipoles here. And you know for a macroscopic drop of matter, about 10 to the power of 23 constituent particles are expected. So in at least 1 mole of a magnet, I can have maybe 10 to the power of 23 magnetic atomic dipoles. So if we want to deal with such large numbers, then we can use whatever we have studied for the random walk problem, even to address questions regarding a magnet. And you see here the number of up dipoles minus the number of down dipoles should give you oppositely pointing dipoles should give you the total magnetization capital M of the system. That's what I have written there. So where in the random walk it was small m was describing the displacement of the man from the lamppost. Here capital M describes the magnetization of the magnet. Okay. So in a similar way, I can find out in the absence of any magnetic field, when an external magnetic field H is 0, the average magnetization will give you 0 from our calculations, and the square of the magnetization will give you the will be given by this 2n. Okay, and then when I have a magnetic field, and even if it doesn't have to point just up or down, it can point in any directions, which I have drawn in the next figure downwards. So the dipoles can be oriented in any directions. In those cases also, I can treat this kind of a toy magnetic model, and with the help of statistical mechanics, And then, since in the absence of field, they can point in any directions, but as soon as I switch on an external magnetic field, the dipoles will try to orient towards the field, and more or less there will be, save some fluctuations due to the temperature, to the thermal fluctuations, they will be more or less pointed towards the direction of the magnetic field. And then this alignment from a non-magnetic state to a magnetic state can be actually studied with the help of the statistical physics. Nonetheless, I should caution you that this kind of magnetization, this phase transition from a paramagnet to a ferromagnet, is in the presence of magnetic field. I can expect these things to happen, but even without the help of magnetic field, I can expect a transition from a paramagnetic state to a ferromagnetic state, maybe with the change of temperature. But in that case, since there are no magnetic fields involved there, we have to take into account the interactions between the magnetic dipoles, which is also very important in addressing questions like phase transitions, because phase transitions are actually called cooperative phenomena or collective phenomena, and phase transitions are never shown without the help of cooperation between atoms and molecules. Sir, I and Abhirup was discussing from where the question arises. How does entropy determine the arrow of time? If time is based on entropy increase, can it be reversed by decreasing entropy? Well, let us discuss these questions at the end of the talk. That will be, because I have not much time left to finish the talk. Let me finish the talk quickly, and then we can take up these questions to the extent that we can within the purview of the talk. It's not possible to address all questions. For example, the arrow of time may not be a... Okay, let's see what can be done. Let's see. Okay, so as I say, the phase transition is a cooperative phenomena. So unless we put in interactions between the atomic dipoles, we won't be able to describe this kind of phase transitions. And we can do that. We can actually put in interactions between the dipoles which are physically meaningful. Okay, and which has been tested over time, and people know how dipoles interact with each other, how charges interact, how magnetic dipoles interact. All these are very well known to us now. How even magnetic dipoles interact with an external field. These are all very known to us, and we can actually put those in our model and then find out the dynamics, the detailed dynamics, from which we can get a probability distribution of the magnetization and so on. And from there can collect all average macroscopic properties which are related to the magnetic properties of the system. So macroscopic magnetic properties, of course, okay, from this system, because the magnetic dipoles, which are the microscopic variables here, the dipole moments should give rise to some magnetic properties which are macroscopic. So we can address. So these are how simple toy models can help us understand very involved issues. So now this could be very interesting. As I said, when I am talking about magnets, the interaction between the magnetic dipoles are well known. How they change with the distance from one another, how they change with the strength of the dipoles, and so on. These are very well known to us. However, when birds are seen to flock in the sky, or when bees are seen to form swarms, then we do not know the way they are interacting with each other. Yet, we can see that birds flock, and the flock often is disorganized. If you just clap your hands towards a flock of pigeons, the pigeons will flutter away in this direction and that in a randomly. So the organized state will soon disassemble, right? Disassemble, right? So this is a kind of phase transition again. They were all moving in a certain direction, and all of a sudden they sort of move in different directions. So this is a real kind of phase transitions happening due to the interaction of the birds and with the interaction of some external fields and so on. Maybe the bees are moving towards a direction where they have scented a flower. They know that there's honey there, so they will move in that direction. If there is no honey, if the honey is exhausted, they can go around in different directions. Or a school of fish can go on hunting for some food in one direction just by the smell of the food within the sea. And when the food is over, they can just disassemble and go in, disorganize and go in whatever directions they like. So these could be very essential. These could be very commonplace phenomena in living systems, which has several similarities with phase transitions in non-living systems. Non-living systems sometimes are called passive systems, and living systems are sometimes called active systems. That is where the term active matter comes up, as I was discussing, where these active systems will take in some energy, maybe in the form of ATP molecules, this adenosine triphosphate molecules, these are the energy blocks, right? So they can use those packets of energy and translate that into motion after metabolism. They use that for their movement and so on. Okay, so all these response to stimuli, these movements are actually a result of transformation of energy from this ATP to a directed motion. Okay, so therefore, we can actually, and this is a celebrated paper by Dixit, which I have already given in the bibliography, in the reference section. You can look it up in 1995 paper, where they have addressed these issues. And due to the lack of an understanding even now about how the birds would actually physically interact with each other in order to form a flock or to disorganize in view of the lack of this understanding, what Dixit did very intelligently was that to think of a very rough, crude behavior. That if I am a bird and if I am flying in a certain direction, and if I see all my friends, my other bird friends are moving in a certain direction, I wish to follow that. And how do I follow that? I actually somehow in my mental mind or through my perceptions or feelings, whatever, I calculate an average of the velocities of all the neighboring birds and I adjust my velocity towards that average direction. My instantaneous velocity is always adjusted towards the average direction of my neighbors. That could be a very satisfying rule that I can assign to the alignment of birds. Can I give this kind of rule? Do you think this is very logical or this is completely illogical to think of? Yes, any comments from the other side? Just maybe I'll take 5 minutes more. Or is it possible to take 5 minutes more?
Yes, sir, you can take, no problem.
Yeah. So if I use that as a rule, then as you can see from the equations that Dixit has written there, the position of the bird, of the ith bird at t plus 1 time is actually the position its previous time plus the displacement that it has suffered, which is measured from the second term, the velocity into time, the time difference, this delta t. There is t plus 1 to t, that time they call it delta t. So v times delta t will be the displacement, and if I add this displacement to the original position xi of t of the bird, I will get the new position xi of t plus delta t. It should actually be t plus delta t instead of t plus 1. Okay, so that is how it should be. Okay, now although this is a way of incorporating a direction of motion, yes, Shumrit is here. Please sort of, say yes or no. So the bird is moving in that direction according to the velocity vi, and this vi is actually calculated by the bird itself by measuring the average velocity of all its neighbors. However, there can be some fluctuations of the birds, maybe due to the interaction of the wind, or maybe because it wants to somehow change its direction a bit temporarily here and there. So there could be fluctuations about this mean direction, right? So if I take an angle theta, I can say that the theta of the bird also changes from a mean average theta, which is on the right hand side. The first term in the second equation is the average theta, which is the average direction that the bird calculates from the direction of the neighbors, plus a delta theta, and that delta theta is some sort of fluctuation that the bird can afford to have. So this together will be the new direction. So once I know this new theta, I know the new direction, and I also know the new position minus the old position, the displacement, so I can get the full position and velocity of the bird. And from there, you see, we can get a nice kind of flocking state from a completely disorganized state to a flock state. If you see all those pictures on the right hand side, you'll be able to see that there is a phase transition going on that can be described by this Wicksec model. Okay, and there are other graphs which I don't want to go through because it will take a lot of time in order to explain all those. So it actually shows how the mean velocity, like the mean magnetization, can be taken as a function of temperature, or the magnetization can be studied as a function of external field. Here, how the mean average velocity, which serves as the order parameter of the problem, can change with either the noise or the density of the system. Okay, and it shows a kind of phase transition as you can see here, from a less ordered state to a more ordered state. Now, similarly, we have studied a problem very recently, not very recently, quite a long ago now, on predator-prey dynamics. You see, where we have two particles, two Brownian particles. I can think of one as bacteria, the other as some amoeba, and so on. And the amoeba is chasing the bacteria to engulf it. And then both being micron-sized objects, maybe one is about 1 micron, the other is around 100 micron. Nonetheless, they are on the order of microns. When they are moving, they are being completely, they are feeling the fluid environment all around, and therefore they are doing Brownian motion. So if I can address the dynamics of these predator and the predator being the amoeba and the prey being the bacteria, which is trying to run from one another. So the bacteria is trying to run from the amoeba, run away from the amoeba, and the amoeba is trying to catch it by sensing a chemical that both of them are secreting. The predator is secreting a chemical, sensing which the prey will run away from it, and the prey is sensing a chemical which is serving as an attractant towards the amoeba, towards the predator. So it's a chemoattractant and a chemorepellent kind of chemicals that are being ejected, that are diffusing in the fluid, with which the two particles are being coupled, the two Brownian particles, the amoeba and the bacteria, two self-propelled particles are getting coupled. And if we study the dynamics, we can again see that there is a crossover from, as you can see, from a short-time behavior to a long-time diffusive behavior, from a subdiffusive to a diffusive behavior in the long run. And we can actually draw a phase diagram for this predator prey, where depending on the strength of the chemical, the strength of the coupling of the predator and the prey with the chemicals, which we define by a small delta, and depending on capital delta, which is the initial distance between the predator and the prey, depending on these, how we can expect a trapped state and an escaped state. So what are the scenarios under which I can expect the amoeba catching the bacteria, and under what scenarios will there be a possible escape from this chemotactic hunting scenario, you can see. Okay, so these are very interesting problems of chemotaxis one can address using statistical physics, and maybe that relates to one of the questions that someone was asking about how the random walk problem can help. There was some question. No, I don't see the question anymore here. Is it in the comment section? Yes.
Yes, I am showing up. I am putting
Yeah.
this in front of you.
Yeah. So how do random walk model helps in understanding? No, the transport property I have already explained. Something else related to cells and their movement. Something was there. No.
Uh, hmm,
In what ways can the study of phase transitions in statistical physics aid in understanding the transition between different states of biological system, such as differentiation of cells? So that is I think I have partially helped in partially address these questions where I can see the state of flocking, the self-organization, we call it self-organization. So even in tumors or in cancer, like in metastasis, all the cells sort of when they become cancerous, they sort of form a flock which can go on invading other tissues of our system or other organs of our living system, right? So this is a kind of phase transitions that the cells are experiencing, and the flocking of birds and the flocking of bees and so on. The Vixit model that I have sort of partially touched upon in gist, not can, is actually helping us to address this kind of problems, this kind of complicated biological problems through detailed simulation studies. Okay, so this is more or less what you say, I guess. Yeah, and this is the bibliography. Okay, so this is the bibliography I have taken some references from,
yeah.
and that's it. Thank you.
Yeah. Okay,
Okay.
sir. So there are a couple of more questions came up.
Yes.
I am
Yes.
just putting in front of you one by one. So this is another one.
Yes. So if I just ask, was the talk helpful, interesting, very boring, very boring, or I mean whatever. I mean, feel free to sort of comment.
Yeah, it was very enjoying and enlightenment.
Okay.
Interesting as well.
How does entropy determine the arrow of time? If time is based on entropy, increase, can it be reversed by decreasing entropy? Okay, so this is partly the question makes sense. The other part which doesn't make sense, I'm leaving it out. Uh, well, when I talk of entropy and I say that entropy increases in an irreversible process, not in a reversible process. If the process is reversible, then the entropy does not increase. It remains constant. It doesn't change. Delta S remains zero. Okay. But in an irreversible process, it increases. What does that mean? For example, if I have particles, for example, this Brownian particle that I was talking about, it is interacting with so many atoms and molecules in the neighborhood, right? So molecule 1 is hitting it in this direction, molecule 2 in that direction, molecule 300 in this direction, molecule 5600 in that direction, and so on. Now, if the Brownian particle is to retrace its position from this part to its previous parts, then all these molecular motions has to be exactly reverted, right? So if there was a disorder that has been gained, in no way I can do away with that disorder, you see, because we cannot actually make the molecules to completely retrace their path exactly and decrease the disorder in the system. So this is in just what an irreversible process could be felt like. Okay, could be sort of understood like. So in any irreversible process, your entropy will increase because the amount of disorder is going to increase and increase and increase, you see.
Okay. Right.
Okay.
Yeah.
What role does the correlation length play in phase transition and how does it change as a system approaches the critical point? Okay, again, good question. Okay, so what do you mean by correlation? So when I think of correlation, so who's asking this? This is Oviruk is asking this one?
Yes.
Yeah, yeah. So, Viru, can you just tell me what do you understand by correlation? So, what to you, what does the word correlation mean? Appears to be just in whatever, even in layman terms. Don't I mean, don't feel hesitated. Even if it is a silly answer, it's okay because it's like an informal thing, right? It's an informal kind. Even if it's a silly answer, don't hesitate to answer whatever it feels right. Yes. What do you mean by correlation? So for me, what I mean by correlation is something like this, Ovilu, is that uh, if I have a Brownian particle, yeah, correlation is associated between two variables. It can be also between one variable at a point of time and the same variable at a next point of time. Okay, so it could be like a velocity correlation. So if I have a velocity of a particle, for example, v of t, v changes with time, right? So as if I have velocity as a function of time of a Brownian particle, then at the next instant of time, t plus delta t, its velocity will change. Why will that velocity change? The velocity will change because the Brownian particle has suffered so many kicks from the environmental molecules and atoms, right? So many bombardments. That is why that will change. And again, in the next step, it will change and change and change and so on. However, the change of the velocity at a particular instant of time and the next instant of time can be related with each other. Why? Because by the time the velocity has changed to v of t plus delta t, the atoms and molecules around this Brownian particle has not completely forgotten their previous behavior. They can carry on with their kicking in a certain direction, right? They have not completely, the randomness has not set in completely. You see? The randomness has not completely set in. So there will be an influence from the previous time steps and so on. However, over time, as time goes on, this randomness will take in, and then the velocity at a very large time and the velocity at present will be completely uncorrelated from each other, completely decorrelated, not influenced by one another. You see? Do you see? So, Bidu, I mean, if you can put your microphone on and sort of interact would be helpful.
Or you can comment it down.
Yeah.
He said
Yes, sir. Yes.
Yeah. So there will be a time after which the correlation will significantly decrease. So that will be called the correlation time. Okay. Similarly, if I think of a polymer is just like a noodle. If I just see like a Maggi noodle, it is something like this, right? So one end of the Maggi noodle I can bring to the other end and I can join. However, if the two parts of the Maggi noodle are very close to one another, it may be very hard for me to bend it and join together, right? Because there is a bending energy and that is related to the orientation of the atoms around. So that is not helping me to somehow bend it completely. It may not be that flexible, right? So there is a length over which the this rigidity would matter, right? So I can call that the persistence length of that molecule, of that polymer, you see. So that will be kind of a correlation length over which the directors of the polymers will be correlated. So these are like correlation length and correlation time. Okay. So what happens near fully phase transition, for example, when a liquid is changing into a solid phase or a solid is changing into its liquid phase or a liquid is changing into gas and vice versa, what happens? For example, I will give you a specific example when a gas is condensing into a liquid, okay? So what happens here, the correlation lengths, they diverge, they start to diverge because what happens when they try to condense, then there will be droplets of several possible sizes which come up, right? And these sizes can range from very small to very large, from very microscopic to very macroscopic as they condense from gas to a liquid phase. Previously, they were all apart, the molecules were all apart. Now they are coalescing, they are trying to condense into a liquid state. So there will be islands of liquids which are very small, there will be islands of liquids which are very large macroscopic. So there will be a very flat, a very broad distributions of these length scales of these islands, okay, of these liquid islands. And that's why we say the correlation lengths, they diverge at phase transitions. And this divergence are generally power law divergence. It is seen that they have very definite power law behaviors, you see. So there are these power laws in which these correlation lengths and correlation time, they diverge. So these are some beauties and some surprises of nature. Also, it has been seen that there are systems which are completely very disparate from one another, very unrelated from one another. They are showing phase transitions, but they are showing the same kind of power laws. The power law, the quantity, the measures, they are very similar. So based on that, we can club these systems, although they look completely dissimilar, we club this system as a class which we call universality class. Okay, so there are several universality class possibles. We say that these kind of phase transitions are characterized by this universality class. That means all systems, however dissimilar, disparate they look like, if they show same kind of critical exponents, these exponents are called the powers are called the critical exponents. If they show the same exponents, critical exponents, they fall in the same universality class and so on. So this is how nature has been built up, maybe by some God, by some thinking God. I mean, it is nice to think like in those terms. Okay. So, how do information transfer and communication between birds affect the decision-making process during flocking, and what mathematical frameworks can be used to model this information flow? Okay, this is a very involved question. I'm afraid I won't be able to take it up in this short duration. But one thing I can maybe tell you in order to see that, okay, if you go to your Google, you can see that there are many videos, and these videos are actually done by scientists where there's a flock of starlings. There's a flock of starlings and they are being attacked by a hawk or a crow or something, a large bird. And you see, there's a flock, and then from the rear, a hawk comes and tries to take away one bird. So as they approach, there is a signal that this bird, which is very close to the hawk, will send, maybe by its way of flying would be such, which is completely different from the neighboring birds, because this bird is under panic. So he will do something, and that will be relegated to the next, because as per the Wicksec model, as per our very crude understanding of the state of affairs, the birds are always trying to calculate average velocities of the neighboring birds and align its direction towards that average velocity. So if there is a disturbance by one of the individual neighbors, that will be transferred to the next bird and to the next and then to the next, and that is how the information will propagate throughout. And then there will be defensive mechanisms that the total flock will take up, seeing those informations flowing around. Okay, so I hope that sort of answers the question to some extent. That is how information flow propagates. Okay, through interaction among the different individuals. How do predation risks influence the structure and dynamics of bird flocks, and what adaptive behaviors? Well, that's what I exactly said this while answering the previous question. There is emerging response to different types of predators. Well, different types of predators is very general comment. So biology is a very diverse thing. So we study specific systems, and there are specific defense mechanisms for different. So for one kind of birds, the defense mechanism could be something. For other kinds of birds, it could be something else, right? For cancer cells, the defense mechanism is something else, and so on. So there's no general answer to that. Okay. Can studying bird flocking behavior inform the development of autonomous drone swarms, and what specific aspects of flocking should be prioritized in the design of the drone algorithms? Okay, so if you want to design a drone, you have to do it for a specific purpose, right? There has to be some purpose, which I may not know of, which maybe you are knowing of, or someone else who is building the drone would know of. So, depending upon what purpose the drone is used for, what kind of dynamics it has to show, accordingly you have to mimic this kind of things in nature, so and study those kinds of things in nature and see how they interact and incorporate those kind of behaviors in your drone. And that's all I can say. Okay. So is that all?
Okay, so there is another one.
Okay, sir, in Brownian motion, we are actually considering one particle and studying its behavior, yes, with respect to the other particle, yes, then trying to generalize it over all particles. Is it correct? No, we are in Brownian motion, what we are trying to do, shuffle, is we can actually consider all particles together simultaneously. All, maybe there are n particles, n could be 100, n could be 200, n could be even 1 lakh. Depending upon your computer system, if you have a good computer system with a large memory, you can actually model about 10 lakhs or even a billion particles, not billion, million particles, even a million particles you can, okay, depending upon but the thing is, you can study all of them and you can take the interactions between all of them. So each particle, if I have 100 particles, one particle is interacting with all the 99 particles, and that will be the Fij term that I have taken. If you remember, if I go back to one of my previous slides on the Brownian motion, here if you see that I don't think there is a laser pointer, something like this, no, that I can use to, you can see the third term. The third term is actually Fj on the ith particle, okay. Or is there a more better Fij? Or if I can take this equation, the dp I dt is equals to Fi external plus the second term. The second term is Fij summation over all j. So the Brownian, one of the Brownian particles, when I take up it, I have to take interactions with all the 99 particles. The second particle, again all the 99 particles, and so on. And so they simultaneously change their positions, feeling the forces on each other, and that is how they go on changing. Of course, there will be a noise term also from the interactions with the environmental molecules. Okay. So does that answer your question, Shuffle? Or?
Yeah, Shuffle, you can write down your answers in comment section, YouTube comment section.
Yeah.
So there is, I think, last one question we have left.
Okay, application areas of statistical mechanics on astronomy. Okay, there are many, like there are these white dwarf stars and so on. So if you go into stars, for example, the sun. If I just take the sun is a star, right? So here I can see Shambhit. So Shambhit, actually, you should actually nod your head if it is yes, and no if it is not. Okay, so the Shambhit, if I take this sun is a ball of fire. Why? Because it has this helium atoms, right? Hydrogen atoms and helium atoms. These are what is sun made up of? I forget. What is it made up of? Sun is made of hydrogen and helium, I guess. Helium also maybe, or only hydrogen. Whatever. So these atoms at a very high temperature, right? This is a very high temperature, and so they are completely ionized in an ionized state, right? Mm-hmm. And in that state, the atoms, if you want to address them, you have to address them individually. Okay? Yes? Do you see this? They are made of atoms and molecules, and they have to take into account each of the dynamics individually, right? Or even if I take collection of them, like a mole of such hydrogen gas and helium gas, which is making up the sun,
Mhm.
then 10 to the power of 23 of them, at least in one mole of the sun, then these atoms and molecules we have to address by quantum statistical mechanics. Because you see, there will be electrons, protons, neutrons, and atoms themselves. They either classify as fermions or bosons. Okay, so there you cannot do classical statistical mechanics at these temperatures where the atomic, where maybe this these kind of quantum things will be very essential, or even at very low temperatures. Although at very high temperatures, I can still think of like classical kind of statistics. But the thing is, there, if you wish to see the expansion of sun or the collapse of a star and so on, then you have to talk about all these macroscopic properties, the full star, billions of them. So here, I cannot actually treat them individually. So there is where statistical mechanics actually comes to help. Okay. Okay, so depends upon what questions you are trying to address in astronomy. Okay, so
Okay.
that's what I.
I think that's all. I
Yeah.
have no more questions left.
Anything else? My
You
question. Okay,
can
that is done. Anything else?
to the audience and viewers how you
Sir,
enjoyed
I
this
am
session.
from probability and statistics background. This application, especially of the random walk and Brownian motion related part, makes sense to me. Okay, so that's overview is what's saying. Anything else? If not, then we can call it a day.
Yes, sure, sir. So thank you, huge thank you to our special
Uh,
uh, today.
yeah, Shomit, I think you are muted. If you were trying to say something,
Yes, sir. Am I audible, right?
I can't hear you. Shomit, I can't hear you.
Uh, I can hear you, sir. Am I audible?
No.
Abhirup, please confirm. Hello, hello. I think I am audible. Okay, I think we can wrap up today.
Ovidu, shall we call it a day? I mean, what is Shomit is trying to say something, but I can't.
I think I
Shomit is
can hear.
audible? No, for me, is not audible.
Uh, I I can hear you, sir, properly. I can hear both of you.
You can hear me?
Okay, so let's call it for today. And until next time, stay curious, keep exploring, and
No,
remember the universe
somehow.
full of mysteries waiting to be uncovered.
Yes, could be a network glitch. It could be a network glitch, but you can hear me? Can you hear me?
Sir, I am talking already.
Can you guys hear me?
Yes, yes, I can hear you, sir.
I can see the network glitch written by Uberu, but I can't